welcome to session 2 of Unit 6. This session will introduce you to the various medical and energy applications of radioactivity in various spheres of human life. By the end of this session, you should be able to state the importance of radioactivity to diagnosis and treatment of diseases. And you should also be able to highlight the principle behind using knowledge of radiation to energy. Let us look at the uses of radioactivity in the medical field. Hospitals, doctors, and dentists use a variety of nuclear materials and procedures to diagnose or monitor and treat a wide assortment of metabolic processes and medical conditions in humans. The most commonly used is the X-ray. The X-ray is a type of radiation that can pass through our skin. So when the bones and other structures in the human body are X-rayed, they will cast a shadow because they are denser than the skin, and the shadows that the bones or these other structures cast can be detected on a photographic film. There are several radioisotopes that have been used to assist in wide variety of diagnostic tests and treatment protocols. The use of radioisotopes is convenient because they can emit gamma radiations. They have a short life or short half-life, and they are emitted from the body shortly after completion of the diagnostic test or treatment. Let us look at radio diagnostic protocols. Now, the radioactive traces can be added to the bloodstream to enable us to monitor the movement of biochemical components in the human body. We can also use the iodine-131, a beta emitter, to treat overreactive thyroids and also to detect internal hemorrhages. Another diagnostic protocol is the use of diagnostic technique in nuclear medicine, which make use of radioactive traces which emit gamma rays from within the body. Now, with this technique, an instrument called a gamma camera produces an image of the distribution of radioactivity in an organ. So by using this camera in conjunction with a computer, the function of this organ can then be closely monitored. Another protocol is the use of positron emission tomography (PET) scan, and this is used to detect cancerous growth in the human body. So mostly this PET is used in oncology with fluorine-18 as a tracer to detect and evaluate most traces. It is also used in cardiac and brain imaging. These traces that are used are generally short-lived isotopes linked to chemical compounds, which permit specific physiological processes to be scrutinized. The traces can be given by injection, inhalation, or orally. Let us look at some therapeutic uses of radioisotopes. One, we can talk about cobalt-60, which is an intense gamma emitter and is used in cancer treatment through direct irradiation. So the cancer cells are irradiated with the cobalt-60. We can also talk about the treatment of leukemia, where phosphorus 32, which is a beta emitter, is injected intravenously, and this helps to treat the leukemia. Again, pacemakers also use plutonium 238, which is an alpha emitter, to regulate heart actions. The cesium-137 is also used to treat cancer, and in doing this, the cesium-137 is encased in a biologically inert material, and then it is inserted into the body, such as into the cervix or the rectum, and this will help to treat cancer in these regions. The gold 198 or iridium 192 wires can also be inserted as implants for treatment of cancer in the tank. Let us look at nuclear power plants. Electricity produced by nuclear fission, that's splitting the atom, is one of the greatest uses of radiation. As our country becomes a nation of electricity users, we need a reliable, abundant, clean, and affordable source of electricity. We are looking forward to when we'll begin to produce our electricity using nuclear fission. We've studied in the past that the purpose of the nuclear power plant is to boil water to produce steam that will power a generator to produce electricity. Now, inside the generator are coils of wire and magnetic field, which will interact to create this electricity. The nuclear power plants are usually fueled by uranium, which emits radioactive substances by fission, and this generates heat. The reactor in which this radioactive reaction takes place is usually cooled using water. However, a small amount of the radioactive substances become mixed with the water, and so the water is passed through several processes to filter and then remove these radioactive impurities from it before it is returned to the environment. Nuclear Regulatory Commission, the NRC, has established a limit of radioactive substances that can be released from a nuclear plant. They established this limit based on an assumption that the public exposure to man-made source of these radiations should be only a small fraction of the exposure that people receive from natural background sources. So the radiations that are received by individuals from these artificial radioactive sources should just be very small as compared to what the individual can receive from nature, since the natural radioactive materials that people receive from nature, they have no control over it. A person that spends a full year working at the boundaries of a nuclear power plant site is expected to be exposed to a radiation that is less than 1% of the radiation that every individual is likely to receive from nature or from natural background sources. So these are your self-assessment questions. Kindly try your hands on them.